Welcome back, Algebra Express. We are in Rockswold 5.1. So in this section, we are going to start combining functions. In 5.2, we will be finding inverses in one-to-one. In this section, we're going to combine functions, and we're going to start combining functions with the four basic arithmetic operations: add, subtract, multiply, divide. So there you see some difference, product and quotient. So we're going to do the four arithmetic operations, and then after we get done doing these four operations, we're going to do something called composing functions or composite function or composition of functions. And so that is a bit different than these four operations, but we're going to start with these four, and they start with a profit example. So a word problem. So the revenue and cost of a product in dollars for sales of X units are given by the data below. So we see X is the number of units, R is the revenue in dollars. Here as X is the number of units and C is the cost in dollars. So they give us two functions and two tables. And so they ask about the profit from the sales of X units is given by, and they say P of X equals R of X minus C of X. And they want us to evaluate P of 2100 and interpret the results. So if I'm looking along here, they give us the definition P of X equals R of X minus C of X. And so if I do P of 2100, this is equal to, and if I'm looking here, this 2100 is taking place of the X. It is an X value. So I want to figure out what R of 2100. And I want to figure out what C. Plugging these things in to my X value. I want to plug it into the X value of my R function, figure out that that is giving me 59,850. I want to plug it into my C function, figure that's giving me 19,500. And if I look at these, I do 59,850 minus 19,500. That's going to give me 4350 or 40,000. So we found P of 2100. Now they want us to interpret the results. So they kind of give it right here. What this means is the profit from selling 2,100 units is this number that we found, which is 4350. Okay, and so we found this thing. This is the way we should interpret these. And now they throw this table at us. So my advice for solving these is to write out your definition. So this is just a bunch of notation. So if we see f of x plus g of x, we can write it with this shorthand notation over here. So if they give you this thing on the left, if they give you this operation, write out your definition, write out the meaning, write out this thing on the right. Okay, and now we want to talk briefly a little bit about the domain. If we're using our f of x and our g of x function, so if there was anything up here we couldn't plug into x, how would that affect our profit? We wouldn't be able to plug it into our profit either. So what this thing is doing is it's going to inherit the domain restrictions that are coming from f of x. It's going to inherit the things that are coming from g of x. And they didn't do this, but if we wanted to rewrite this, we could rewrite p of x as maybe like r minus c of x. It would be like this operation and this meaning, right? We'll talk a little bit about this, more about this on the next page when we get an example. But this is sort of like when you want to go out on a school night, and you ask one of your parents and they say no, and then you ask another one and they say yes. Overall, you're probably not going to get to go out if you do something like that. So it is as strict as like kind of the strictest parent. So sometimes you can think about it's inheriting restrictions from its parents. So it's inheriting both restrictions from both f of x and f of x. So we got to look at both of our functions. If there's anything we can't plug into this or we can't plug into this, we can't go plugging it into operations with them in there. And again, we'll get an example on the next couple pages. And we'll talk about their domains and how those things get influenced with some solid examples. If we have f divided by g of x, or f of x divided by g of x, ditto, right? We're going to have the same restriction. And we get an added restriction here. There's an extra little thing we need to check. When we start dividing by things on the denominator and things in the bottom cannot be 0. So g of x cannot be 0. And extra little stipulation we got to check. Okay. Now an example. If we get f minus g of x, the first thing I said, and if you don't write this down, I'm going to pretend like I don't know what you're doing. This looks like f of x minus g of x. This is the definition. If I see this operation, this is the meaning or the definition. This is the first thing you should write. If you write this thing, we know f of x looks like root x. G of x looks like root x minus 5. And I'm supposed to subtract these two things. There is something that I'm going to do. Every time I plug something in, I'm going to put parentheses. Here, especially when we're subtracting. Because if you don't put it, there's a good chance to subtract root x. But this is plus 5. There's a good chance you might miss that distribution and adding 5. So we're subtracting this function, this entire function from this entire function. Good idea, again. And every time I plug something in, I'm putting parentheses around it. So it is good practice to do. I'm looking along here. I wanted to combine like terms. I see a root x that's positive. I see a root x that's negative. So root x minus root x is going to give me 0. There's no more root x's there. I have a 1 plus a 5 is going to give me 6. Okay, so this thing looks like, maybe not the thing you're expecting, but it looks like 6. So if this is a function and it's equal to 6, you might realize this is like a constant function. This is like a flat line. Okay. But I want to talk about its domain. I want to talk about f and its domain. I want to talk about g and its. So if I'm looking at f, this looks like root x plus 1. And we talked about this before if we're talking about the real numbers and graphing things in the real numbers and being in the real numbers. This thing in the square root cannot be negative. It can be 0. It can be 1. It can be anything higher. It can be anything higher than or equal to 0. I have the same thing over here for g. I have a square root here. I have the same restriction. Now I want to think about my domain overall. So it is as strict as the strictest parent. So if we combine an x is greater than or equal to 0 and an x is greater than or equal to 0, you might have figured this out. But it's the same restriction. We have to make sure x is greater than or equal to 0. So this looks like a line, but it has this restriction coming in. And so that might seem a little weird, But let's go and graph these things, and maybe we can talk a little bit about why it's doing the thing it's doing. So if we look at root x plus 1, that is like just the common root x function just moved up 1 unit. Is one way to think about it. If I think about root x minus 5, it's the same graph, we're moved down 5 units. If I do f of x minus g of x, so what I'm doing is I'm subtracting function values. So if I'm looking here, I'm going to have 0, 1, and what, 0 minus 5. If I subtract their function values, what I'm doing is I'm subtracting not their x values, but I'm subtracting their y values. So what this is telling me, between 1 and negative 5, there's a difference of 6, is what this is telling me. And so this is giving me this minus this. And so what this is telling me is that all along here, these things are going to be exactly 6 units apart. And then we talked about the domain restriction, right? So this thing, my root x does not go left to 0. My root x here does not go left to 0. So if I'm subtracting these two lines, and I try to come over here to the left of 0 and subtract the 2 lines, you might notice, hey, there's no lines to subtract. So that's why this thing does not go left to 0. We're not going to get it from subtracting these 2 lines. So it looks like a flat line. Follow them along, probably. That's where that line is coming from. It's coming from subtracting these 2 lines. So it does not go left to 0 because the 2 lines we use to form it aren't not going left to 0. So this is what I'm talking about. It is inheriting the most strict. So if I started toying around with this, well, I'll move it to the right one. So if I move this thing over, right, this line is also going to move over. Okay. Now we look at fgx. See these two numbers, two letters written together. Fg, this means f times g of x, or f of x, and we're going to multiply by g of x. So I'm looking at f of x as root x plus 1, and I said it every time I plug it in, I'm going to write parentheses, root x minus 5 is another thing. If I'm looking along here, the first thing I'm multiplying is root x by root x. That should give me a single x. The next thing I'm doing is minus 5 root x's. I'm doing plus 1 root x. And I'm doing minus 5. So I'm doing some distribution. And again, this thing is coming from root x times root x gives you a whole x. There are some like terms I might need to combine. Oh, excuse me. Okay. Next, I have a minus 5 of these, and I have a plus 1 of them. That means overall I have a minus 5. You might look at this, you might say, is there any way I can simplify this? I don't think so. X. That is what this thing should look like. My domain. So my domain is still as strict as my strictest parent. It should look like something like x is greater than or equal to 0. And we also see the restriction. The restriction's actually in this one, right? It's not in this one. It still stays in this one when we multiply things through. So this one might be a little more obvious. We still have that restriction. This one, not so much. Okay, and then the last thing I look at is f divided by g of x. So I see this thing. The first thing you should write is what the heck this thing means. This thing means f of x divided by g of x. Okay, so I want to know what my f of x is, root x plus 1. My g of x looks like root x minus 5. Okay. So I'm not sure what the book is going to do. If you did this and you told me root x plus 1 over root x minus 5, I would be happy personally. The book likes to rationalize what they might be doing. They might be multiplying that thing by the conjugate. We get x. Root x. By the conjugate, we get x. X minus 5. Minus 25. We would get something like x plus 6 root x plus 5 over x minus 25 on the bottom. So sometimes books like to rationalize the denominator. They do that by multiplying by the conjugate. So I would not necessarily expect that for the work that you turn in for me. If you show me this, this is good enough for me for this section. So I want to think about my domain. So my domain is going to from its parents. So that one, I think we probably see that, and we're like, was in the first two. It's definitely got to be in this third one here. The other thing, I have to check that my denominator is not 0. So what is going to make my denominator 0? When root x minus 5 is equal to 0, that's like when root x. Well, my pin's out of link. Wow. Okay. I'll do it with marker. That's like when root x is equal to 5. So if root x is equal to 5, how do we get rid of a square root? We have to square it. So x will be equal to 25. And so this is another domain restriction. X cannot be 25. So if we look back at this, x has to be greater than or equal to 0. X cannot be 25 is what I should say. Or I could just write maybe a comma here. I have to include both of these restrictions. All right, so write out your definition. If you write out your definition on these guys, I think you will probably get them correct. Most of the time when people are getting things wrong, they're not writing out their definitions. There's a few other ways people has to be not writing out their definitions. So f plus g of x equals f of x plus g of x. If it's 3 here, it's f of 3 plus g of 3. So I'm looking here, I'm looking at f of 3, and write out your steps. Don't try to do too many things at once. We do this, and then we do composite of functions, which is done pretty differently, and people get the two concepts confused. So if I see a plus, or I see my arithmetic operations, I will want to write them out, and I want to use that x value. I'm using that x value twice here. So if we look at all these definitions, the operation or this notation, this new notation that they're giving us for these functions, we only see that x value once and we want to write it out twice. When we get to composition of functions, it will not be that way. But if I write out my definitions, the only other thing I have to do is go to my graph and grab out my values. So f of 3, I'm looking along here, I'm going to 3, and I'm going to my f function. That gives me a y value of 1, so I'm doing 1 plus, and my g of 3. So now I'm coming along here to 3. I'm looking down at my g function, and this is a minus 2. So if I add these two things together, I believe these two are going to give me a minus 1 overall. So f of 3 plus g of 3, or f plus g of 3, is a minus 1. So what we're trying to get at in general, and I'm not sure, I don't know if I mentioned it earlier, but we have, basically we're starting with 2 functions. We could have more functions, but we could add, subtract, multiply, divide them. We can do all these things with 2 functions. And what we're doing is we're creating like a third new function, right? We have a revenue, we have a cost, we have r minus c, but we can also call that thing p and think of it as a new function. So we're going over ways to sort of like create new functions from 2 existing functions. And so this gives me a minus 1 up here. If I want to do f of g of 0, or not f of g, f times g of 0, sorry, is f of 0 times g of 0, f of 0. So I go to my 0 and my x. I go to see what my y value is a value of 2. My g, I go to my 0. I go to my g function. My g function is a minus 3. If I do 2 times a minus 3, this is going to be minus 6. Okay. So f times g of 0 is minus 6. So we got one more example. This is student practice, so hopefully you're trying these things out on your own. First thing I want to do, I want to look at this. I want to write out my definition. So f times g of x times g of x. My f of x looks like 1 over x. My g of x looks like x plus 3. If I want to combine these things, I could always kind of think about this thing as maybe being over 1, but if I'm multiplying these things, I'm going to get the x plus 3 on top. I'm going to get the x on the bottom. So what this looks like is x plus 3 over x. If I want to think about my domain restrictions on f and my domain restrictions on g. So I want to think about these domain restrictions. So if I have 1 over x, there is one domain restriction here. The x cannot be 0. If I have x plus 3, this is, and think about maybe this thing graphically, that's just a linear function. Is there any number we can't plug into a line that's just a normal line? We can plug any real number into this thing. We can add 3 to any real number. It's not going to mess it up. This is anything and everything. So if you go to one parent and they can tell you can have anything and everything, and you go to the other parent and they say, well, you can't have 0. Guess what? Overall, you're not going to be able to have 0. So this inherits it from my f of x function, but it's also in the end product here too as well, right? So it comes up kind of twice. It may not come up in the end product. Remember, the one on the previous page did not. So it may or may not, who knows? Anyway, we have another one. F of x over g of x. So again, write out your definition. F of x over g of x. This is my definition. Now I'm just following my definition and plugging things in. So my f of x looks like 1 over x. I'm dividing this by what? An x plus 3. Okay, so I know this one you should really simplify. We don't really want fractions in fractions. If I have 1 over x here, I don't want this fraction in there. So how do I get rid of a 1 over x? I got to multiply by its reciprocal of like x over 1 or just by x. So I'm multiplying by x top and bottom. And if I do that, I get 1 over x and x over 1. This should give me a 1 on top. And I should really get an x and an x plus 3 on the bottom. You can also do copy dot flip. We divided, right? We divided 1 over x divided by x. 1 over x divided by x plus 3 over 1. You can also do this like we did rational division, right? If we flip this thing, it's going to end up on the bottom. Okay, so I have 1 over x and an x plus 3. Now I want to talk about my domain. So my domain, it's still inheriting this thing where x cannot be 0. And if I look here, if I look at this first step, it might be a little more obvious here, but it's also here. There's another thing we can't have, and that's where my g of x is equal to 0. So x plus 3 cannot be equal to 0, which is the thing we see in the denominator, so that is matching up with what we're saying. So x cannot be minus 3. So we have 2 domain restrictions. There's an added one because we're dividing here. Okay, and now we want to evaluate things from a graph. So again, if we're evaluating things and they give us the shorthand notation, we want to draw out or write out the definition of a minus 4. That from minus 4. It's telling me from the definition of this thing. So I want to look at minus 4. And my x, I want to go to my f value. That's giving me a y value of 2. And I want to subtract what g is at a minus 4, which I look along here to minus 4. My g is a minus 2. I want to subtract a minus 2. So overall, what this is going to give me is a positive 4. Same thing with this other function. I want to write out the first thing, if I don't see it, is the definition of this thing. F of a minus 2, that by g. I'm going here to a minus 2. my f of a minus 2 is right here. My y value here is 0. I'm doing g of a minus 2. So I go to my x value of a minus 2 and drop down here my g of a minus 4. If I'm looking at this is the thing you got to think about maybe for a minute. Think about pizzas and people and what the heck I'm asking. This is the number 0 over a number is 0. So this one is 0. If the 0 is on bottom, it's undefined. Okay. Okay, so I'm not sure why it did this, but for some reason, for every composition of functions, for every composition symbol, it put a box. It should be like f of g, little circle-looking thing. There's a little hollow circle that we put between there. So if we see f of g, this means compositions of functions. And so far we did 4 arithmetic operations. The thing that people usually confuse this with is multiplication. This is not multiplication. This is different than multiplication. So make that note in your head somehow. But composition is we're going to plug one function into another is the best sort of way to describe it. We're putting one into the other. And so we want to look at evaporation rate. We're going to start off with the word problem. And I got a little snowman melting away there. So they're looking at the hour of the day and they want the evaporation rate. And they give us 2 functions that give us the temperature and then they give us the evaporation rate based on the temperature. So one's temperature based on hour of the day, one's evaporation rate based on temperature. So if we look at the hour of the day, 12 o'clock, you might notice your temperature is 68. And if we want to know the evaporation rate when things are 68, the evaporation rate is going to be 4.7 measured liters per minute is what it says. Okay. So I go here to 12, it's giving me 68. 68 is giving me 4.7. So I have an x value of 2. I go here. 2 is giving me 83. 83 is giving me 20.9. 4 o'clock is giving me 90. 90 is giving me 42.2. 6 o'clock is giving me 83. 83 is 20. 8 o'clock is giving me 68. 68 is giving me 4.7. And so what did we do? Composition, and again, they did not get the symbol right on this for some reason. Everything else got correct on here, but like F and G. F and G should have that little circle in between them. So what we did, we composed E of T. So again, just to re-emphasize this, let's throw a variable here. If we go ET of X and we use this sort of definition, what we did is we did E of T of X, where X is our temperature. Sorry, X is the hour of the day. Sorry, got it wrong. So if we look at this, how many times are we using this X? How many times did we use the hour of the day value? We used it once to get to temperature, and then we used temperature to get to evaporation. So there's a weird sort of thing that's happening. We went 12 gives me 68, and 68 gives me 4.7. There's a sort of weird thing that's happening. We're going from X to Y. This Y becomes a new X in this one, right? So we will see it. We'll see it again. But T of X gives me a temperature. I plug the temperature, which is a Y value here, into this one as an X value. So my Y from the first one becomes my X in the next one. We're plugging one function into the other. So going over a few examples to get this a little bit more solidified. And they don't talk about the, okay, so let's jump to the domain on the next one is what it looks like. So finding the domain on these composites is a little bit different. There are two sort of things we have to look at. It will inherit restrictions. And then after we do the thing, right? After we do the composite, we're going to have to look for new restrictions. There's no sort of easy way to get it. We just have to do it. We have to do the operation and see what it has in the new formula. There could be new things depending what the function looked like. And again, the inherited restrictions are f of x and g of x, right? It's parent functions. It's the strict parent. All right, so let's do a few and see what it looks like if we want to do f of g of minus 5. F of x is root x plus 3. G of x is 1 over x squared. So f of g of minus 5. Here is where I'm talking about we want to rewrite our definition. If you rewrite your definition, f of g of x is f of g of x. You keep these things in the same order. You basically drop the sign. You put a few parentheses in the place. Okay, and so this is a little bit weird because typically when we read things in English and every other language, we read things left to right. When we do these functions, compositions, they actually kind of go in like a reverse order of like what we typically read things in. We start with the rightmost function and we start reading them out leftward. So it is a bit of a different orientation, and I know sometimes people struggle with it because it's a bit backwards. But it's manageable if you write it out. If we write this thing out and we write out our definition, I'm looking along. Better color. Here's my red. I want to look on the inside out. So I want to start working this inside out. I look on the inside. G of a minus 5, that is something I should be able to fill in. Okay. So what is G of minus 5? G of minus 5 looks like I take G and plug a minus 5 into it. Looks like 1 over minus 5 squared. So we've done this before, plugging in my X. So my F stays there. But I want to do G of minus 5 and evaluate it. This looks like 1 over minus 5 being squared. I can simplify this out a little bit. You're probably already yelling at me. This is 1 over 25. So now I go from the inside out. I started with f of g of 5. That means f of g of minus 5. This means I'm plugging in minus 5 to my g function. I do a little bit of simplification. Now I'm left with this thing, f of 1 over 25. So now I'm looking back at my function. My f of x looks like this. I'm plugging 1 over 25 into my f function now. So this looks like I have a root of 1 over 25, and I have plus 3. This I can simplify a little bit if I do root 1 over root 25 plus 3. This is what, 1/5 plus 3, I believe. I guess I could go ahead and like combine it to an improper function. This is 3.2 or 16/5. If you gave me this, I would be pretty happy. This is 3.2 or 16/5. These are all the same thing. Okay, so that is compositions of functions. So we have a few more examples. For the function f of x equals x squared and g of x equals 1 over x minus 9, find the following and its domain. Okay, so going right away at this domain, if we're composing it with two functions, look like this thing. Right away, I know this has no domain restrictions. I know here my x cannot be 9. So right away, I'm pretty sure x cannot be 9 is going to apply to both of these. It's got at least that much for its restrictions. There might be more. If I want to do f of g of x, let me write the right symbol just so we can see it. I want to write out my definition. Looks like f of g of x. Now I start from the inside out. I go and I look inside here. I look at g of x. I'm looking at just g of x. My g of x looks like 1 over x minus 9. That takes care of my g of x. Now I'm looking here. Now I have this thing that looks like 1 over x minus 9. F of x is I take that thing and I square it. So I take 1 over x minus 9 and I square it. I could probably simplify this a little bit. This is really the same thing as having the x minus 9 squared on the bottom if we write it out twice. One over x minus 9 squared is what this thing is giving me. And so we wanted to look at this and look at domain restrictions. So there is a domain restriction here. The x cannot be 9. We're getting that maybe twice. You can think about it, right? But x cannot be 9. We've already accounted for it. It's there. Okay. So I did f of g. Now they're trying to get at a property here. So if I do f of g, or if I do g of f, right? So this is the commutative property. We've talked a little bit about this. But if I do g of f of x, let's write it out with the correct symbol instead of the crazy box that they decided to put on there. And I want to write out its definition as g of f of x. Okay, so I'm looking along here. I'm looking in the inside. I want to work the inside out. So I will look at my f of x. My f of x is the first thing I want to plug in. That looks like x squared. Now I'm plugging in an x squared to my g function. So my g function looks like I do 1 over x minus 9. So I'm plugging in x squared here. I'm plugging in an x squared here. So what this should look like is 1 over, and this thing looks like x squared minus 9. Okay, so this is pretty good. I'm going to do one thing. This down here is the difference of squares. So I think I'm going to go ahead and factor it just because it might make things easier in just a second. But this is 1 over x squared minus 9. And so we want to look at our domain. So our domain cannot be 9. That's one of them. But if we're doing x squared minus 9, this is really like an x plus 3 and an x minus 3. I really have two more restrictions here. The x cannot be minus 3 or x cannot be positive 3. And then the other question, if I do f of g or if I do g of f, doesn't matter what order I do these things in. Are these the same thing? They are absolutely not. And again, I can do this in expanded notation. This is like 1 over x minus 9 and x minus 9 over here. If we want to write it at factored, this is like 1 over x plus 3, x minus 3. They are not the same factors, right? They are not the same number. These things are giving us different results. So order matters when you do composition of functions, what order we compose these functions in. All right, so we have to look at the parent functions when we do the domain. We have to look at the end result. And now we have a graphical interpretation of these things. So you might want to notice I only use my x value once when I do composition of functions. So f of g of 1 you write out your definition means f of g of 1, and you want to start with the inside out. So g of 1 is the first thing I see on the inside. So I'm looking at the x value of 1. I'm finding my g gives me a y of a minus 1. So g of 1 is giving me minus 1. Now I want to figure out what f of minus 1 is. So I go to my x, where it's a minus 1. I look up here at my f value. This is giving me 2. So write out the definition, work it from the inside out, and then write out these steps. Don't confuse this with multiplication, right? When we use multiplication, we would be using the x value twice. Here we're only using this x value once. We plug it into one function. It gives us another value. This guy's y becomes this guy's x's, and we get another y value. All right. That was A. We want to do B. So we haven't done this so far, but you don't have to compose two different functions. You can actually compose the same function with itself like this. So we got some GOG here, GOG, of a minus 4. What this means by definition is g of a g of a minus 4. So we want to go to -4. I want to know what my G value is at a -4. My G value at a -4 is 0. So this thing is evaluated to 0. Now I want to know what G of 0 is. So now I'm going to 0, and my X value, I'm looking here at G. This is giving me -2. Okay. And the last part, C. This is G of F of 3 means G of F of 3. Write out your definition. We look on the inside, F of 3. So I want to go to my X value. I want to see what my Y value at F is, which is 2. This thing in the inside is evaluating at 2. I still need to do my G function. So G of 2, now I'm looking at 2 here. My G at 2 is the value of 0. Okay. So now we have one last example. This is student practice, so should be getting these. For the function 1 over x squared and g of x equals x minus 1, find each of the following in its domain. So f of g, and then we have to do what? G of f, and then we have to find the domain. So this one's pretty similar to the one that we did previously. It's a little different. F of g of x. F of g of x is what it should say. If we write this out, we write out our definition, f of g of x. We look on the inside and we start working this thing inside out. So the first thing on the inside I see is g of x. I can rewrite that as an x minus 1. And so now I'm doing f of x minus 1. Those are the same thing. I want to plug in an x minus 1 into my f function. So everywhere there's an x, I'm going to replace it with an x minus 1. So instead of 1 over x squared, this is going to look like 1 over an x minus 1 squared. I didn't do my domain here, but if x squared cannot be 0, this is going to give me a restriction that x cannot be 0, and it's going to give me that restriction twice. This thing has no restrictions, it's just a line. So right away, I could probably just go ahead and plug this into both of these domains. We know this is a restriction on both of these things. X cannot be 0 on either of these things. Okay. The other thing I want to check for is I'm going to do, okay. I have 1 over x minus 1 squared on this one. So the other thing I want to check for is this one. So if I'm looking at the domain on restrictions on this one's going to give me x cannot be 1. Here I'm looking at g of f of x. So if I'm doing g of f of x, I want to write up my definition of g of f of x. I want to look sort of like inside out at this thing. I'm going to start here. Instead of f of x, I'm going to write 1 over x squared. And so now I'm going to plug this thing into G. G says I take x minus 1, so I take this thing that looks like 1 over x squared, and then I'm subtracting 1. Okay, so this thing looks like 1 over x squared, and we're subtracting 1. So I'm looking at my domain restrictions here. So x cannot be 0 here. We've already accounted for that. And this is the final problem that we're doing here. And so next time we will talk about inverses in one-to-one. And so we have talked about what adding, subtracting, multiplying, dividing two functions, and now we've talked about compositions of functions. So I will see y'all soon. Take care and study hard.